Hello and welcome to the first video in a new series on system identification with Julia. So first of all, we might ask ourselves, what is system identification? And for the purposes of this video series, it's the art and science of relating the input of a dynamical system to the output with some kind of mathematical model. And the complexity of that mathematical model can range from anywhere from a linear time-invariant system to something extremely complicated like a nonlinear PDE or a black box neural network, something like that. But we're essentially trying to fill in the question mark here in this box with some mathematical model. And typically I will use the letter U to denote an input and the letter Y to denote measured output. And an interesting thing to point out here is that this dynamical system typically has some form of state comprised of several state variables, but that is not something we can observe. Instead, we observe or measure some kind of output. We might be able to measure some state variables, but they are still corrupted by noise. So there is still a clear distinction between the state and the output. So just as an example, here we have some interesting input and output data. In the top plot we have the output, in the bottom we have the input. So system identification would be concerned with figuring out what would be a good dynamical model to describe this data set. And we can see that it looks fairly complicated. Both input and output starts at 0 here, and then the input goes up to 1 and stays there for a while. But the output does a rather complicated dance with several kind of swinging steps. And then the input goes to -1 and the output follows, and then the input starts switching faster and faster and faster, and we see that the output gets messier and messier. And then after a while, here we see when we swing the input at a certain frequency, here we see that the output appears to become larger in amplitude. So there is a lot of complex and interesting phenomena that happens in this data set, and we would perhaps be interested in trying to figure out what would be a mathematical model that describes this relationship. And I can give you a hint, even though that this is looks very complicated, it's actually a linear time-invariant system. So it's in some sense the most basic form of a dynamical system you can imagine. But even that rather simple class of dynamical system can produce this rather complicated looking behavior. All right, so a little outline of the series. It's kind of an introduction to system identification. We will focus slightly more on how to do things rather than why. I expect you yourself to know why you would like to do this. We will also focus on practice rather than theory, although we will mention the relevant theory every now and then. So I would like to say that this is not a replacement for a complete university level course on system identification, but it's nevertheless something to get you started, or if you already have a background in system identification, this course will tell you how you do things, or one potential way of doing things in Julia. So we will cover everything from beginning with the identification of linear time-invariant models. We will talk about how we can track time-varying parameters. We will find the parameters that fit the data of a nonlinear system. We will discover unknown physics. If we don't know how to model the system, maybe we can discover a reasonable model. And we will talk a bit about uncertainty quantification. And this list of topics may actually grow with time. So to start off, why do we want a model? Why do you want a model? We might use models for a lot of different purposes, right? And our system identification has to be guided by the actual purpose of having a model in the first place. So maybe we want to do design simulations, and we want to simulate some system before we have built it. And if we haven't actually built the system, then of course it's hard to do system identification on it. So that's typically not a use case where we're interested in system identification. We might want to use a model for prediction, so we want to know what is going to happen in the future, or have a reasonable guess of what's going to happen. We might want to do control analysis and design. Maybe we have some kind of system we want to control, and we want to know how do we actually implement a controller and tune that and so on. And we might want to use a model for that. We might also use models to try to figure out if something is going wrong with the system. Imagine you have a factory with lots of complicated and expensive machinery. And maybe you would like to detect before something goes wrong that something is about to go wrong and fix it before it becomes too expensive to fix a disaster. We can also use models for what's sometimes called virtual sensing or more generally state estimation. So we want to figure out, we can't measure everything in our system, but we want to figure out some property or some state of the system as it operates without being able to measure that particular thing. And we can use the available measurements. Maybe we can measure something else that is related to what we care about. And together with the model, we use the measurements to figure out the hidden or the virtual measurement. All right. So before we actually start with system identification, we should always think about what do we already know about the system. Very often we have a rough idea of how the system behaves. Maybe we have some model already, but we're missing the parameters and so on. And that's kind of an important first step to selecting a model. So in the worst case, we know absolutely nothing about the system. We don't know any equations that describe it. We just want to fit the model. And that's depicted here on right in the top little diagram. That's often referred to as a black box estimation. So we just have the input and the output and we know nothing. Just find a model that fits. All right, so that would be black box estimation. And then we have some forms of shades of gray here. So the more we know about the system, the more we should make use of that knowledge, of course. So maybe we know some parts of the system. Maybe the system is composed of some physics that we are well aware of and is easy to model. But maybe there are some parts that are not very easy to model, or maybe we have created a model and we see that it doesn't perfectly fit and we don't know why. Then maybe we would like to kind of fill in this missing physics here. Maybe we would like to do some model discovery or just fit an arbitrary black box model here so that the total model fits the data. Or maybe we know most things about the system. Maybe we have a very good mathematical model, but we are uncertain about the parameter values. And in that case, we want to calibrate the parameters of our model so that the model will fit the data in some sense. So here I use the Greek letter theta to denote the parameters. So these would be referred to as some form of gray box identification in the language of system identification, where black box is a completely unknown structure of the model, whereas a gray box is that we know some kind of structure. All right, so then we go back to why do you want a model? So we said that you might want to simulate or predict or do control or something like that. And we have a number of different complexity classes of models. And before we dive into this little table here, I should say that this is of course grossly oversimplified. System identification and modeling and simulation in general has a lot of nuance to it that deserves to be considered. But for now, we just give a very, very rough overview. So we have here in the first column, we have a linear model. Typically, we don't use those for design simulation unless this system we're designing happens to be well described by a linear model. But we assume that we cannot do that. The linear model will not be good at predicting something globally either. And when I say globally, I mean across the entire state space. But we might use a linear model for some local prediction around a particular operating point. And linear models are also very successfully used for control. So if we want to keep some output variable at a fixed level, that is usually okay to do with a linear model. But if we want to do tracking control, so we want the system to actually move and transition from one state to another, then perhaps the linear model does not describe the system sufficiently well in the entire state space to make use of that. So I use this orange little symbol to denote that, yeah, maybe it works, maybe not. And the same for fault detection and predictive maintenance. If our true system is indeed non-linear, maybe we will have difficulties using a linear model here. Then we have a linear plus plus, a class of models here. And that's kind of a model that is essentially linear, but there is some twist to it. Maybe it is time varying. Okay, so that's still a linear model. Maybe it has some parameters that vary with time. Then it's not really linear, right? But we can still consider it a linear model, but the parameters somehow vary. We can also consider linear models that have some form of nonlinearity in a very structured form. Maybe there is a nonlinearity on the input, but then it's just a linear system. And those can be estimated rather efficiently. And they are quite useful for a lot of things. We can also consider some kind of the other side of the spectrum here, a nonlinear black box model. So that would be an arbitrarily complicated model for instance, a neural network. And we typically don't use those for design simulation. But we can use them for prediction and control and tracking and all of these things. And we can always take a nonlinear model and linearize that if we need a linear model for some reason. And then, of course, the most sophisticated and nicest model in some sense to have is kind of a mechanistic model where you have equations that describe exactly how your system behaves. At least that's very nice to have if that model happens to fit the data well. That can be much easier said than done to arrive at such a model. In fact, it might take years to develop such a model. But if you have that, of course, you're in a good position. So sometimes we like to go all the way there. Right, but of course, the complexity of both modeling and estimating models increases as we go to the right here. A linear model is very easy to come up with, and it's easy to identify the parameters of. Whereas a nonlinear mechanistic model can take, as I said, it can take years to actually arrive at an accurate model there. So it's a trade-off. All right, so we also have a workflow for system identification. And here that workflow is depicted as a never-ending cycle. And that sounds pessimistic, and it's not quite that bad. But it is typically an iterative process where you start perhaps by deciding on some kind of model structure. Perhaps you know background information that it's a reasonable model of this system. Then you collect some data, all right? You or one of your colleagues or friends collect data. Then you use that data to fit the model and you validate that. And typically the first time you go through this process, that validation will fail in the sense that the model didn't really fit the data very well. So then you're back here at deciding a new model structure. Maybe you need to add terms to your model if you're modeling equations. Maybe you need to increase the state dimension if you have a black box model, and so on. Maybe the problem was that your data, there was something going on when you recorded the data and so on, and you need to iterate here. And sometimes this iteration can go on and on and on for years, and I actually have experience with that, and that's not uncommon. It's almost always an iterative process. And the first step here is typically deciding on a model structure. So then you of course need to ask yourself, what are you going to use this model for? Are you going to use it to derive a linear controller in a particular operating point? All right, then maybe a simple linear model is fine. Are you going to use this to predict the failure? Then maybe there is other considerations you need to take into account. What kind of fidelity do you need? Do you just need a rough model to do something simple and quick and dirty, or do you need something where you can predict to a very, very tight tolerance? All right, that will of course influence what kind of model you choose. Are there disturbances affecting your system? So very often the simple picture of this dynamical system with an input and an output that I showed before, it just doesn't hold, because you don't actually observe the true output. You observe the output with some measurement noise. Maybe that's just electrical disturbances, but maybe it's the sun is shining on your temperature sensor, for instance. So that's quite annoying. And maybe there is also some disturbance that affect the actual dynamics of the system. So if you imagine an airplane, the wind is obviously not just affecting the measurement, it's affecting the entire system, right? So if you have wind and you don't measure that wind, that is going to mess with your identification of the airplane dynamics. And another consideration is if you want to estimate a very high fidelity model, you need very good identification data. You need data that actually exposes the behavior of the system. And maybe that's just very difficult to obtain. Maybe it's too expensive to run the experiment, maybe it takes too long time and so on. So if we can't obtain the required data, then perhaps we need to limit the flexibility of the model. So the next step then is of course collecting some data. So we have a number of problems that can arise when we try to do that. So I said it can be expensive or difficult. And in the best of worlds, maybe it's I go out in the lab and I run the system, being it a robot or some temperature heater or or something like that, and that takes me an hour. All right. But it can also be that you need to get approval, and then you need to decide a date, and then you need to run an aircraft, all right, and it costs $1 million. And then of course you need to prepare that experiment very well, and if the experiment goes wrong, then you're stuck with bad data and you have to kind of redo the experiment. Maybe the experiment is that you crash a car and record the signals, and obviously that's going to be very expensive. The data you collect must also expose the behavior of the system that you try to model. If you only send slow inputs, slowly changing inputs into the system, then you can only hope to model the kind of behavior of the system, how it responds to slowly varying inputs. If you send fast changing inputs into the system, then perhaps it will behave very differently. And if you didn't see that behavior in your training data, you can't really hope to also model it. Another aspect is that you also want to avoid exposing behavior that you don't want to model. Maybe you know that if I send a particular high frequency into this system, it behaves very strangely, and I don't want to model that because that's not relevant to how I'm going to use the model later. Then you typically want to avoid to excite that behavior in your training data. And then sometimes we are collecting data in closed loops, which means that there is some controller that is actually deciding on what the input is. And that comes with a lot of caveats, so that actually makes the input correlated with the noise, and that's theoretical difficulty as well as a practical difficulty. But sometimes you don't have a choice. If your system is unstable, maybe you need a stabilizing controller before you can actually run any experiment, and then you're stuck with actually collecting data in closed loop. But the important thing is that we know that the data is from closed loop, and we make sure that we handle that properly. All right, so if you find yourself in this situation here, where you are the blue figure, and your friend says that, yeah, here's the data, I have collected it for you. Then the appropriate response is that you need to know everything about how that experiment was performed. And I say here every single detail, and maybe that's exaggeration, but it could very well be important. So what could possibly be wrong when you record some data to perform system identification on? So the first question you ask is, of course, what are the units of measurement used in this data file? Are you using SI units, or are you using some non-SI units? So my favorite is per mil of rated gearbox torque. All right, so that's a very non-standard unit, and you also have to know what is the rated torque of the gearbox to be able to convert that to SI units. But this is very common, that people use units that are suitable for what they are going to do with the data, and that may or may not be suitable for you. So you need to know obviously what units were used and convert it so it fits with your expectations. Of course, you need to ask them, maybe did you calibrate the sensors? Very often there is some calibration procedure. Maybe the sensor is temperature dependent and so on, and there has to be some calibration. And if you don't do this, then there is part of the model that is not gonna fit because your idea of how the model behaves, the system behaves, is not correct because there is an additional sensor dynamics that you were not aware of. Did the system make any strange sounds when you performed the experiment? So very often when we collect data for system identification, we use the system in a way that we maybe don't normally use it. And if the system sounds very strange when we did our experiment, maybe we are actually exciting dynamics that we don't want to excite in our data. And this obviously applies to mechanical systems. And if you have a non-mechanical system, a chemical system, maybe you need to find some other way of figuring out, is the system behaving different compared to what you're used to? Are there any cables hanging loose? Okay, so that's actually from my previous experience. A cable can both, if the cable is affecting the movement of a mechanical system, the cable adds additional dynamics, all right? And of course, if the cable is slightly loose, you might lose some measurements and have corrupted measurements in other ways. And that can happen when you collect data for an experiment. Does the system have any extra tool attached at the moment? If you're identifying dynamics of a robot, there are usually things attached onto the robot. Perhaps the robot is holding a mass, perhaps it's holding a tool, Perhaps there are a welding gun attached on top of the robot or something like that. And all of these things can add additional dynamics that you need to be aware of when you build and estimate the model. Did the sun shine in? That sounds silly, but if you're estimating a model of temperature being affected by a heat pump, then obviously temperature, sun shining in will add a lot of heat to the building, and that will disturb your model or your system. And you need to be aware of that. Was it windy? So if you're estimating the dynamics of an aircraft and it's very windy, that will obviously affect. So then you need to be aware of that. Did someone slam the door? So if you're using an accelerometer to identify some kind of dynamics of a mechanical system and someone slams the door, then you might pick that up in the accelerometer data. And if you don't know, if you're not aware of this disturbance, maybe you try to figure out a model that fits that, but you shouldn't do that, of course. That's just a measurement disturbance in this case. And that's obviously important to know. The last one here is a bit of a joke, but there are so many things that can go wrong, and you need to kind of be aware of all of these things, both you that estimate the model and your colleague that collect the data. So in the best of worlds, you will actually be present. If you are estimating the model, you should probably try to be present when you collect the data and collaborate with your colleague to make sure that the experiment is performed in a way suitable for system identification. Right, the next step is fitting a model, and we hope that this is the last step, but very often it's not. So we of course need to select some method or algorithm to fit the model on the particular structure we have chosen. And there are tons of different options. We support tons of different options in JuliaHub, and subsequent videos here will try to guide you through that selection process. And then once we have fit a model, we obviously need to validate that it works as we intend and with the accuracy we demand and so on. And to do this, we might simulate the system, or we might try to perform some prediction. I will go into detail what the difference between those two are. And maybe we would like to analyze the residuals. So the residuals here mean the error that the model makes. Is there a pattern in the errors? If there is, then maybe we can model that pattern. Or maybe we decide that that pattern does not need to be modeled because it was a consequence of the measurement setup or something like that. But very often this validation kind of returns failure, that your model is not up to your requirements, and then you kind of take another loop in this wheel, and that's quite common. All right, so this concludes the first introductory video, and in subsequent videos we will start to actually perform some system identification. All right, thank you.